So welcome to class number 2 for Chem 324. So before I dive into today's course material, I just want to get an idea of whether you guys have gone to the tutorials that were offered. Did anybody go? Sorry? There's several times. They're on the Moodle course page. They haven't started yet. Okay. Okay. Yeah. Okay. Well, I'll check in with you guys next week to see how they go. Anyway, so for tonight, I will be going over the mostly review of the reactions that you learned in Org 1 and 2. Hopefully, most of it is review for you guys. If it's not, please let me know. Okay. So first, this is from Klein, Unit 7. Basically, you were introduced to nucleophilic substitution and elimination reactions in this chapter. So essentially, this is taken from the summary at the end of the chapter, and they basically summarize all the reactions that alkyl halides can go through with regards to nucleophilic substitution and elimination. So which of these reactions shown here are referring to nucleophilic substitution? Anyone? This one, yeah. How about this one? Are these nucleophilic substitution? So this one is nucleophilic substitution, yes. How about this one? Yes, this is also nucleophilic substitution. This one? Yes, as well. Yeah. Okay. And that's, so yeah, so there's these four. So essentially, this is just to summarize that you can do nucleophilic substitution with many different nucleophiles. So here you have methoxide acting as a nucleophile. You have thiolate that can be a nucleophile. You have acetate that can be a nucleophile. And then finally, you have cyanide that can be a nucleophile. Are we all clear on that? Okay, so this is nucleophilic substitution, but you learn two different kinds of nucleophilic substitution reactions. So is this SN1 or SN2? Yes, I saw someone put up a 2. So yes, these are all SN2 reactions. And the reason for that is because we are dealing with a primary alkyl halide, right? So when we are talking about an SN1 reaction, we go through a carbocation intermediate, which I'll talk about later. And primary alkyl halides aren't prone to do that because primary carbocations are unstable. So what ends up happening is your nucleophilic substitution, the attack of your nucleophile and the displacement of your leaving group happen in the same step, which makes it an SN2 reaction. Do you guys remember that? I'm not seeing as many nods as I would like. Okay. In any case, it is expected that you guys would know these reactions. So if you do need any more supplemental reading, I would point you to Klein chapter 7, which goes through all of these SN2 reactions and the other ones that we'll talk about later as well. Okay. So we also have Another SN2 reaction here. So here, hydroxide can also act as a nucleophile. But when we generate the alcohol, that is the product from the nucleophilic substitution, we can also turn it back to the alkyl halide by reacting it with HBr. So essentially, do you guys know what reaction that is? So in the presence of HBr, HBr is a strong acid, right? So what would happen to the hydroxyl group? Yes. So you would get this as an intermediate. And then you also have, it's a strong acid, so you have free dissociation of the H plus and the Br minus. So you have Br minus here too. That can displace that protonated alcohol to regenerate the alkyl halide that you start out with. So this is, what kind of reaction is this? It's still an SN2 reaction because you don't have, you have attack of the nucleophile and displacement of the leaving group happening in one step. You don't go through a carbocation intermediate. So only when you go through a carbocation intermediate do you, is it a tertiary, sorry, is it an SN1 reaction? If it's happening in one step, then it's an SN2 reaction. Okay. All right, so let's see, let's just go around over to this region. So with an alcohol in hand, you can, and we briefly talked about this last time actually, you can react it with what is called a tazol chloride, or generally they're called sulfonyl chlorides. So compounds that have a general structure that look like this. In the case of tazol, your R is equal to a para-talo group. So essentially like that. So this toluene portion is at this part of the molecule for tazol chloride. And the reason why you want to change it to a tazolate is because you want to, in the case of oxygen containing electrophiles, you want to change this group here into a good leaving group, because without protonation or the formation of a good leaving group, OH is not really prone to be a good leaving group. So in order to convert an alcohol either back to a bromide or by converting an alcohol to other substrates that can be a product from an SN2 reaction, you have to turn it into a tazolate first. Okay. So this reaction, converting an alcohol, primary alcohol, to a tazolate, what kind of reaction is that? Okay, that is also an SN2 reaction. There's a lot of SN2 reactions on this page. Basically, you have, I'll draw it over here. You have two lone pairs on your alcohol, and that basically just attacks the sulfonyl, the sulfur, and then it displaces the chloride, and then that generates your alkyl tazolate. I know I'm showing you mechanisms here, but I don't expect you to have to know these for the purposes of tests, because I expect you to already know these. But judging by the silence that I'm hearing in the crowd, I feel like you don't really or maybe you've like forgotten it a little bit. So yeah, so I really suggest you guys not focus on mechanisms, but remember the reagents that are used to afford each of these transformations. So for instance, if I want to generate an alcohol from an alkyl halide, know that you have to react it with sodium hydroxide in order to get displacement of that bromide. So I need you to know starting material, reagent, and product, because that is essentially what you need to tell me when I ask you to make more complicated molecules, say starting from an alkyl halide, and I want you to go through an alcohol intermediate and then more synthetic steps subsequent to that. So remember the reagents, the starting materials, and the product. You don't need to know the mechanisms for this because you should already know the mechanisms. But if you don't, review it. Right, so you can regenerate the alcohol from the tosylate just by reacting it with sodium hydroxide again. So it's a very similar reaction to what I've shown here, but instead it's with OH acting as the nucleophile and your tosylate being the leaving group. So this is also, therefore, an SN2 reaction. And then finally, the remaining two reactions, which form an alkene, are a different class of reaction. Does anybody know the name of that reaction? Yes, and the E stands for elimination, right? So these two reactions are elimination reactions, and specifically they are E2 because they involve the primary alkyl halide and we don't go through carbocation intermediates. Just gonna write that down for you guys. So I'm just going to read what I just wrote. So SN2 and E2 reactions do not go through carbocation intermediates, and the attack of the nucleophile and displacement of the leaving group occur in the same step. And the reason why is because a primary carbocation something like that is unstable, very unstable. So that is not likely to happen. Any questions so far? No? Okay. I'm just going to show you guys briefly the mechanism for an elimination reaction, E2. So you have a proton here. Well, you actually have two protons here, but I'm just going to draw one for sake of clarity. And basically your base, which is terp-butoxide, abstracts that proton, which breaks that carbon proton bond and pulls electron density to make that double bond. And then we break the carbon leaving group bond. So we in fact also form tosylate. We'll well, technically, we form tosylate and terbutanol, which is from the protonation of that terbutoxide, which we have as a base, just to make sure our chemical reaction is balanced. And it's the analogous thing with alkyl halides. In this case, alkyl bromide, you have, instead of having your tosylate as a leaving group, you have bromide as your leaving group. Yeah. Zoom in. Oh, okay, sorry. Is that better? I would put down the blinds, but they don't work right now. Yeah, it's kind of annoying, but the sun should set soon. Yeah. Yeah, so T terbutyl, which is equal to that R group. Yeah, I've seen like T-bu, I've seen that as well. Sometimes the T is also italicized. It's hard to show when I'm writing. But yeah, I would say either are accepted. Any other questions? Okay. So, oh yeah, I also wanted to point one more thing. At the beginning of the semester, I said in our course, our focus will be on carbon-carbon bond formation. And the reason why that is kind of a new development for you guys is because most of the reactions that you've learned so far are just functional group interconversions, and you're not really learning about how to create more complicated, more complex carbon-carbon structures, which is essentially the foundation of organic chemistry. You want to build more complexity into your molecules, right? So whenever you have a carbon-carbon bond forming reaction, it's always good to point it out. So here is actually one that you've learned already. When you use cyanide as a nucleophile, you are in fact forming a carbon-carbon bond in an SN2 reaction. So this is just one example of that. We good? Okay. So with tertiary alkyl halides, we have actually, I've been saying tertiary and primary, like you guys already know what that is, but do you guys know what primary and tertiary means? Okay, at least you remember that. Good. Okay. So the thing with tertiary alkyl halides is instead of seeing SN2 and E2 reactivity, we see SN1 and E1 reactivity. So I'm just going to put a little blurb in the bottom of that of this slide. So they go through a carbocation intermediate. Which essentially means that the carbon leaving group bond breaks first. Yeah. And then you have the carbon nucleophile bond forming. So you'll see me maybe in the future abbreviate LG as leaving group. Nucleophile as nucleophile, or NU as nucleophile. I don't know if other profs have also done that for you guys. Yeah. Okay, so you're familiar with that. And the reason why it's stepwise like that is because we have tertiary carbocations. They have these electron-rich CH groups that can help donate electron density and stabilize the positive charge on a carbon. So that's why tertiary carbons are more prone to exist in a carbocation form. Okay, so let's go through all of these reaction arrows like we did for the previous slide. So what reaction is this? Going from the tertiary alcohol to the tertiary alkyl halide. Okay, how about we think about the mechanism? So we have an acid, HBr. Our first step, like before, would be protonation of that hydroxyl group. And that would generate a good leaving group like that. But because we have a tertiary carbon this time, we can form the carbocation intermediate. So we actually go through that carbocation intermediate. Which looks like that. And then our bromide can attack the carbon. I'm just going to draw it more clearly to give us the alkyl halide as the product. So if this is not an SN2 reaction, what is it? Yes, it is an SN1 reaction because it goes through the carbocation intermediate. How about the reverse reaction, like the if we react an alkyl halide with water to give that? Yeah, it is also an SN1 reaction. How about this reaction here? Reaction of an alcohol with tosyl chloride to give the tosylate. Is it SN1 or SN2? It's actually an SN2 reaction. And the reason why is because we our alcohol here in this in this example here, our alcohol, the OH is acting as a leaving group, and this is the electrophilic carbon, right? But in this case, when we protect the tosyl chloride, protect the alcohol with tosyl chloride, this is actually acting as a nucleophile and tosyl chloride is acting as the electrophile. So just to remind you guys what tosyl chloride looks like. Essentially, you have okay, maybe I'm going to redraw it because that's going to be a little confusing. So this time your oxygen is acting as a nucleophile, which is displacing the chloride on the electrophile to give you the alkyl tosylate. In the previous example, your alcohol is the electrophile. And your nucleophile is the dissociated HBr. So the nucleophile electrophile roles are switched between these two reactions. So don't just rely on context clues, I guess, because I did say this page was mostly SN1 or E1 reactions, but in case that's not really true, you really have to kind of objectively look at the reaction that is in front of you, try to reason through what mechanism you are, or what mechanism that it goes through in order to give you the desired product. Otherwise, you would misidentify what reaction is actually happening. Are we clear on that? Okay. Okay, so alkyl halides can also form alkenes under different reaction conditions. So if we use a hindered base, we get, well, first of all, let me draw out the protons that can be removed. So we could have this proton being removed or this proton being removed. I'm going to use blue just for elimination reactions, so that that's clearer. And when we have our deprotonation occurring here, I'm using B to represent just a generic base with a lone pair. You're going to see me do this probably a lot throughout the semester. So your base can attack either here to abstract that proton or there to abstract that proton. If it goes through the first one, then you'll form a double bond at this position. If you remove this proton, then you will form a double bond at this position. So that's why, depending on what base you use, you can actually get different stereochemistries of your alkene. So if you use a bulkier base like terbutoxide, it's got a lot of steric hindrance at that position. So this base would like to deprotonate at a region that is more sterically accessible. So here, this is like a secondary CH bond, and this is like a primary CH bond. So primary has less sterics, which is why if you use terbutoxide, you would preferentially deprotonate at this position to give you an alkene that looks like that. And we call this, we call this less substituted alkene because it only has two substituents. We call that the Hofmann product. And conversely, if you have a not so sterically hindered base, this is just OH minus hydroxide. We don't have any alkyl groups kind of blocking the way. So this can more readily deprotonate at this position here to give you the Zaitsev product, which is the more substituted alkene. So we have 1, 2, 3 substituents on this alkene. It's more substituted than this one, which only has 2. Any questions on this? Is this familiar? Do you guys remember this? Okay. I think I need to turn on the lights. Let me figure this out. How do I turn on the lights? Is it here? Is that good? Is that too bright? Okay. Okay. So these are actually E1 reactions as well, because the first step of this reaction actually isn't the base attacking or abstracting these protons here. It's actually, so I'm just going to erase it and redraw the true mechanism just so that you guys have that. Because it is still a tertiary alkyl halide, our first step is actually formation of the carbocation intermediate. And then we have abstraction by the base either there or there. So this is like a primary CH, more accessible. This is like a secondary CH, less accessible. So terbutoxide prefers to attack here, whereas OH minus can attack there. Are we clear on that? It was basically just redrawing what I explained to you like a few seconds ago. You can also have analogous reactions from the alcohol instead of the alkyl halide. And from the alcohol, you just use acid instead of base. And this is also an E1 reaction, just specifically an acid catalyzed dehydration. But essentially, an alkyl tosylate under similar reaction conditions as before can also form either a Zaitsev product or an Hofmann product, depending on what base you use. And the reasoning is the exact same. Because you end up going through the same carbocation intermediate. Because your first step is essentially breaking the carbon leaving group bond and generating the carbocation intermediate. Any questions? Yeah. Sorry, you're mumbling. I can't really hear you. If you do a hydride shift, what would you get? So I'm just going to redraw. So where would your hydride be coming from? What are you suggesting? Like that one? So just like that, something like that. So, well, it wouldn't go the other way around. You're already at the most stable carbocation at this stage because you already have a tertiary carbocation. This would not be favorable because you would then have a primary carbocation. Your H would go there, right? So there wouldn't be a driving force for that because your most stable species is already the tertiary carbocation. Any other questions? Do we have a lot of review that we need to do on our own time? Okay. All right. The tutorials will also be very helpful in this regard. So I would definitely go if you need some more review. It's really important that you guys kind of have these reactions almost like second nature to you because you have to apply them in syntheses later on. And if there are any sort of deficiencies in your understanding, then it's not going to come to you as easily when you see any sort of synthetic target. So it's very important. Okay, so just one more thing, just wanted to add that this is also Klein Unit 7. Okay. So alkenes, the reaction of alkenes is covered in Unit 8. This is from the summary at the end of the chapter. So let's just go through systematically reactions 1 through 10 and just kind of figure out what's happening. So 1 and 2 are kind of related reactions actually. 1 is addition of HX across a double bond, and that gives you the halide at the more substituted position. Whereas if you react an alkene with HBr in the presence of a peroxide, then you actually get the reverse selectivity to give you the bromide at the less substituted position. So when we have reactivity, when we have HX addition across a double bond and we have a situation in which we can form 2 different products, do you remember what those products are called? Does the term Markovnikov sound familiar? Right. So this here would be the Markovnikov product. So as I was saying, it's the X, which is equal to chlorine, bromine, iodide. These are all just halogens. X is typically short form for all of the halogens, often excluding fluorine because it has very weird reactivity. So generally those halogens. And the Markovnikov product has it on the more substituted carb. Because you can imagine if we add HX across this double bond, the X, the halide, can go either on this carbon or on this carbon. But Markovnikov product essentially states that in this reaction, the halide goes on the more substituted carbon. Which therefore means that this reaction here forms the anti-Markovnikov the bromine is on less substituted carbon. Again, you should already know the mechanism for that, for why you see that selectivity, but I won't ask you for it, but you should know it. Question? Actually, these reaction conditions are specific for HBr. The reason for that is kind of beyond the scope of this course, but yeah, typically this is just for the formation of alkyl bromides. So the reason why I emphasize in one way, in one reaction condition, you can get the Markovnikov product, and in the other, you can get the anti-Markovnikov product, is that this gives you a lot of control over where you essentially want to put your alkyl halide for subsequent steps if you need to build more complicated molecules. So it's important to sort of memorize what conditions give you which desired product. Okay, so moving on, we have another pair of related reactions. This time, instead of installing an X group, we are installing hydroxyl groups. And similar to before, in reaction 3, we formed the Markovnikov product by putting the OH on the more substituted carbon, whereas reaction 4 puts the OH on the less substituted carbon. So we can get the Markovnikov alcohol in 2 different ways. Either just an acid hydrolysis, shown here, of the alkene can get us to the Markovnikov alcohol, or we have these reaction conditions here, which are called oxymercuration, demercuration. And it's very important that you show them occurring stepwise. So step 1 is mercuric acetate and water. Step 2 is sodium borohydride. Because you end up forming this 3-membered intermediate with the mercury, which then needs to be reacted with sodium borohydride to give you the final alcohol product. Once again, I don't expect you to know the mechanism for that, but you should have already learned it. Just basically remember that alkene, these conditions give you alcohol on the more substituted carbon. And this reaction is called oxymercuration, demercuration. The reason why maybe sometimes you would prefer using this over this is because sometimes you might have other functional groups on your molecule that are sensitive to acid. So this is a more selective way to just get the reaction that you want to occur between the alkene, on the alkene to give you the alcohol. So once again, this is Markovnikov. So to get the anti-Markovnikov alcohol, we use borane and THF with peroxide and base, and that is called hydroboration oxidation. And like with oxymercuration, demercuration, you have to show both of these steps occurring sequentially in order to get from the alkene to the alcohol. Additionally, for this reaction, along with a few of the other ones that we'll see, they have this plus En. So this plus En just means that you're also forming the enantiomer, because essentially this alkene is planar and you can have approach of your OH from either above or below the face of the alkene. So you actually form the enantiomer as well with this reaction. So that would look something like that. Next, we have reaction of an alkene with H2 with a platinum catalyst. We could also use a palladium catalyst or a nickel catalyst. There's also palladium on carbon that you might have seen before. So all of these are just heterogeneous catalysts to do a hydrogenation. So this is catalytic hydrogenation. And when you use heterogeneous catalysts like this, both of the hydrogens that you're adding to those carbons add onto the same face. But in this case, because you're not forming enantiomers or stereocenters, when you add hydrogens to these positions, you're not making new stereocenters, which is why they don't show plus en here. Most of the time when you're dealing with hydrogenations, they won't be, even though the H's add on the same face, they won't necessarily generate stereocenters, but you should always kind of keep that in mind that they add on to the same face of the alkene. Yeah? In? You're welcome. Any questions? Okay, you can also add Br2 across the double bond. And that gives you the bromides in an anti relationship, which also, of course, you can have the opposite enantiomer as well. This is just alkene bromination. You go through a bromonium ion intermediate. I don't know if you remember that, which is why you have that anti relationship in your product. I'm just going to write down bromonium ion intermediate. Just so you know that that's what happens. And this compound here is called a halohydrin. So that reaction is very creatively just called a halohydrin formation. And it basically goes through the same bromonium ion intermediate as alkene bromination, but instead of the second bromide attacking the bromonium ion, you have water ring opening the bromonium ion instead. So that ends up giving you the alcohol here on the more substituted carbon and the bromine on the less substituted carbon. This reaction here, which uses RCO3H, do we know what this functional group is called, generally speaking? It's a peroxy acid. So a peroxy acid can react with an alkene to give you an epoxide intermediate. Do we remember what an epoxide looks like? Yeah, it's a 3-membered ring, 2 carbons with an oxygen. Yeah. So this reaction basically goes through an epoxide intermediate followed by opening of that epoxide by water to give you your 2 hydroxyl groups added next to each other. And then analogously, you can have syn addition of your 2 OHs under 2 reaction conditions. They're both oxidations. You can either use osmium tetroxide followed up with sodium bisulfate. I think that is sodium bisulfate and water. And that gives you 2 OHs on the same side as opposed to on the opposite side. Or you can use potassium permanganate in the presence of sodium hydroxide to give you that same product. So either would be acceptable in like a test situation. So this is syn dihydroxylation. And anti-dihydroxylation. The syn means that they're on the same face of the molecule, whereas the anti means they're on the opposite face. And then finally, we have ozonolysis. And ozonolysis might look a little scary at first because this here looks very different than this here. But essentially, what you can think about it is you're just chopping this alkene bond in half, and then you're adding oxygen atoms on each end of those carbons, of these carbons. So you can essentially kind of, oops. Think about it as like that. So if you chop the alkene in half, you have something that looks like that. And then you just put oxygen atoms on it. So that is still in its sort of like 6-membered ring configuration. But if you redraw that into this linear chain, you would then get, that essentially. So let's just do a carbon number check here. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Yeah, so that's essentially the same thing, just drawn in a weirder way. Yeah, question? So you're asking about this reaction? Why doesn't the peroxide act as a nucleophile?
Well, it's a radical reaction, so it's not a nucleophile, right?
Right.
Why is it that the ER radical acts and not the OR radical?
That's a good question. I'm not too sure actually.
Okay.
I would probably say bromide has a longer, it can exist as a radical for longer, just because its larger atomic radius can stabilize being, it has a longer lifetime as a radical. You probably, because just with the nature of radical reactions, you do form a lot of side products with that. Like, I'm sure you've learned like propagation reactions in under radical conditions. So I think you do get those kind of side products as well. Yeah. Any other questions? Yeah. Here it's halohydrin formation. This, this compound here with the hydroxyl group next to a bromide is called a halohydrin. Okay, so how are we feeling here? Like, is this a lot? Are you guys overwhelmed? Yeah, that's what I was worried about. Okay, so let's move on to alkyne reactions. Yeah, question? Yeah. Sorry, what are you asking about? Which one are you talking about? Oh, okay, so we're talking about this here. Well, alkenes are planar by definition. So both the face that's facing you and behind the screen, those both faces are equally accessible by reagents, which is why for most of these reactions, you also form enantiomers. Yeah. All right. Any other questions? Hydroboration oxidation. Now, this is where I'm not sure whether you've like learned all of this. Did you guys learn alkyne reactions? Some of these? Okay. I feel like you guys all come from like different backgrounds for some reason. Like why is that? Did you guys all take it take org 1 and 2 at different times with different profs? Okay, well that just makes my life a lot harder. Okay, so we'll just systematically go through all of these reactions like we did before. So first, to generate alkynes, we can generate them from either geminal dihalides or vicinal dihalides. So this here is a geminal. And this here is a vicinal. Basically, these two terms, geminal means that the two substituents are on the same carbon, whereas vicinal means that they're on neighboring carbons. So your X, again, is usually bromide, but it can be chlorine, bromine, iodine. It's important that you use excess sodium amide because you end up generating the deprotonated alkyne after step 1, which means that you have to reprotonate it during a workup process to get to the desired product. So you need at least 3 equivalents of sodium hydride for this. The first to remove the first HCl or HX, and then the second to remove the second HX, and then finally the third to deprotonate to the alkanide ion. But I mean, you could just write excess and then that's totally acceptable. Don't want to make you guys memorize more than you already need to. And then we can do the reverse reaction, which is called a hydrohalogenation. Basically, hydrogen and halogen is being added across the triple bond to give you back the geminal dihalide. If you use excess HX, you can get back to the geminal dihalide, but if you just use 1 equivalent, you can just add 1 equivalent of that to give you the alkene there. So this is just stopping the reaction after the addition of 1 HX. So this is also a hydrohalogenation. Alkynes can also be transformed into carbonyl compounds. And depending on what reaction conditions you use, the oxygen either is added onto this carbon, in this case here, or the oxygen is added to this carbon in case number 5. So I'll just talk about 4 first, where we have the oxygen being added to this carbon. So this is just called an acid catalyzed hydration. It goes through an enol intermediate. And in next week's lecture, we'll talk about keto enol tautomerism. But basically, this species here, this enol intermediate, tautomerizes to give you the product shown here. You can also kind of think about this as the Markovnikov product. because your oxygen is being added to the more substituted carbon. The analogous reaction 5 that I mentioned before, this is called a hydroboration oxidation. You've seen that for the alkenes before. Essentially the same reaction conditions as that. And again, this reaction goes through this intermediate here. Once again, it's an enol, which then tautomerizes to give you the aldehyde there. And then you can have addition of halides across the triple bond. Just one equivalent would give you just the dihalide. So this is just halogenation. Note that it's one equivalent, or you could just use excess, and that just completely adds across the triple bond and then the double bond to give you that product there. This is also a halogenation. Ozonolysis of alkynes are a little bit more complicated than the ozonolysis of alkenes, but essentially you still have kind of like chopping apart the bond right there to give you a carboxylic acid on the side of the molecule that has the R group. So that's there. And then the remaining carbon just forms CO2, which leaves your reaction, goes into the atmosphere. So this is sort of the true product that you form. It's a way to kind of truncate alkynes to generate a carboxylic acid. So ozonolysis. So these are all reactions that alkynes can do in one step. We also have multiple step ones here. So alkynes, once again, in the presence of sodium amide, we can get deprotonation of this alkyne proton to give us an alkanide, kind of like what I shown there. And then with this carbanion, you can react it with various electrophiles to form carbon-carbon bonds. So this is another way that we can form carbon-carbon bonds. Rx is basically just like any sort of alkyl halide. Alkyl halides are what we saw near the beginning, the first two steps, the first two slides that I discussed earlier. So this is a way to generate internal alkynes from terminal alkynes. And then we can do various hydrogenations with alkynes just to completely saturate them or partially saturate them. So like before with the alkenes, we can do just a catalytic hydrogenation. Also, we can use other metals as catalysts as well. The same ones for alkenes, and that would completely hydrogenate your alkyne to the saturated alkane. But we can also do partial hydrogenations, either with Lindlar's catalyst or with sodium and ammonia. And that can give you either the cis alkene or the trans alkene, depending on what reaction conditions you use. So Lindlar's catalyst is basically just a poisoned catalyst. Poisoned meaning there's impurities inside the catalyst to kind of limit its reactivity. I'll be talking more in detail about that later on, so you don't have to worry about that too much. But just know that with Lindlar's catalyst, you can get a trans, sorry, that's not trans. You can get a cis alkene. And then with sodium in liquid ammonia, because it's liquid ammonia, this is actually a really low temperature reaction. They don't indicate it there, but This is called a dissolving metal reduction. And because this doesn't involve any sort of like heterogeneous catalyst and we have the reaction happening in solution, we prefer the formation of the more stable alkene isomer, which is trans. Any questions on alkyne chemistry? Okay. Okay, before we go to our halfway break, I just want to talk about the oxidation state of carbon. So I'm sure you've learned in your other courses, oxidation and reduction in chemistry have very specific meanings. So loss of electrons is known as oxidation. Gain of electrons is known as reduction. Have you guys heard of the Leo says Burr? Yeah, so that's kind of a way to remember that. But this is sort of saying the same thing in different words. Oxidation, we can also describe carbon atoms that have lots of heteroatoms as having a higher oxidation. Which conversely means that the lower number of heteroatoms, which means more hydrogen atoms, equals lower oxidation, and in other words, more reduced. So heteroatoms typically like nitrogen, oxygen, all the halides, they're typically more electronegative, right? So they withdraw electron density away from carbon, which is why they end up oxidizing that corresponding carbon. Whereas hydrogen is more electropositive than carbon. So when you have more hydrogens, that means you have a lower oxidation number on a carbon. So when we calculate an oxidation state of carbon, essentially, I'll write it down first, and then I will go through with you guys. So when we're calculating the specific oxidation state of any carbon in a molecule, for every hydrogen atom that is connected to that carbon, we subtract 1 for the oxidation state. For every heteroatom that is attached to that carbon, we add 1 to the oxidation state. And any other carbon atoms that are connected to that carbon atom don't change the oxidation state at all. So I'm just going to walk through some examples. So this is just methane. So we have 4 hydrogens attached to this carbon. So this carbon has a -4 oxidation state. Essentially, each of those hydrogen atoms contribute -1, and we have 4 of them. So that's why it's -4. So this carbon here, we have 2 hydrogen atoms attached to it. They're not drawn, but it's understood that they're there, as you know. So that gives us -2. We have 1 oxygen atom attached to that. So that gives us +1. And then we have this carbon here, which doesn't add anything. So in total, this is -1 oxidation state. And then this one here, there's 3 hydrogen atoms on it that I didn't draw, but are assumed are there. So that's -3. And we also have the 1 carbon, 1 other carbon that it's attached to right there, which doesn't contribute anything. So that has an oxidation state of -3. Just gonna move everything aside a little bit. I'm going to go through all the oxidation states of oxygen. So we have our aldehyde there. Just going to focus on this carbon. We have 1 hydrogen right there. For the double bonded oxygen, we count that as 2 oxygens. So 2 oxygens. And then we have 1 carbon with the neighboring carbon there. So that's -1 + 2 and 0, which gives us a net +1. And then finally, carboxylic acid. We have 1, 2, 3 with neighboring oxygens, and then 1 carbon right there. So that's +3 and 0 to give us +3 overall. So you can see typically when we compare between ethanol acetaldehyde, acetic acid, we are increasing the oxidation state by 2. So the difference between this carbon here, -1, compared to this carbon is +1. So that's a difference of 2. And then between this carbon and this carbon, between this carbon and this carbon, it's also a difference of 2. So that refers to the electron pairs that you are kind of losing in the oxidation state. So the reason why it's important to kind of have these oxidation states in your mind is that it helps you kind of identify what sort of functional group transformation you need to do for synthesis. I'm just going to write that down. Yeah. Mm-hmm. Yeah. 1, 2 means that there's 2. 1, 2, 3, 3 oxygens. Any questions on this so far? So this is kind of to link to the concept of oxidation ladders, which basically ranks subsequent reductions or subsequent oxidations and organizes them into like a ladder essentially. So this is just like what I showed in the previous slide, where we go from the alkane to alcohol to aldehyde to carboxylic acid. Between each of these compounds, you have a difference in oxidation number of 2. So you have -3 to -1, that's 2 plus 2. -1 to +1, you also another difference of 2. And +1 to +3 is another difference of 2. So when you go up the ladder, you are essentially performing a series of oxidations. And when you go down the ladder, you're essentially performing a sequence of reductions. So just to reiterate, oxidation refers to loss of the electron relative to carbon. So reagents that can perform oxidations are usually, well, they're oxidants. They're called oxidants in general, but the oxidants that you should be familiar with are chromium-based reagents. So here we have PCC. We also have chromic acid. So oxidants include chromic acid. And then reductions, you might have seen this as well. Sodium borohydride, lithium aluminum hydride, they're all hydride-based reagents. And that sort of makes sense. If we think about reduction as an increase of H atoms, when we add hydride to it, we are essentially doing a reduction. Yeah. Chromic. So this is sort of one oxidation ladder involving alcohols to carboxylic acids, but there's kind of like a more complex one, which is a more complete picture of all the reactions that you should have learned. I think it is really hard to see. So I'm going to try to zoom in as much as I can. We've mostly talked about everything in this bottom portion here. So I had mentioned alkene chemistry and how we can turn that into alcohols and alkyl halides. So anything that happens along the same row, that is not an oxidation or a reduction. That is that's like a redox neutral process. But anytime you go vertically upwards, that would be an oxidation. And then anytime you go vertically downwards, that would be a reduction. So this is sort of a way for you to categorize in your mind what reactions are necessary to get to what functional groups. So anytime you see an alkene, you can think, oh, okay, it's just one step away from an alcohol. But if I want to get to an aldehyde from an alkene, I actually have to do an oxidation to get to that point. So I would invite you to maybe take some time to go through all of these arrows and make sure that you know what reactions they are. I did talk about a lot of them already. I didn't talk a lot about carboxylic acid interconversions. I'll talk about that after our break. But most of the things in this area, at least, and here as well, we had already talked about. And we'll be talking about the rest of that later in the class. So let's take a break for now and then continue in like 15 minutes, so 7:35. Fifteen minutes. Okay, yeah, so I just wanted to check if you guys learned that yet, because we'll also be talking about carbanion chemistry a little bit later on. But yeah, just essentially know that alkanes can be converted to alkyl halides by UV light, and the reverse reaction is essentially a hydrolysis of a Grignard reagent to give you back the alkane. We'll talk about carboxylic acid interconversions later, but for now, we're going to focus on this part of the oxidation ladder. So that involves oxidation of alcohols. So oxidation, as I had said before, just essentially means gain of oxygen or loss of hydrogen. And that's essentially what is happening to this carbon atom as we move up the oxidation ladder. So we have one oxygen in this alcohol. Now we have two, and then carboxylic acid stage, we have three. So we can directly generate a carboxylic acid from a primary alcohol in two ways, both of which are based on chromic acid. So you really would only need to memorize one of these, whichever one you prefer. But one is with sodium chromate in the presence of sulfuric acid and water. Or you can do chromium trioxide in the presence of water and a solvent like acetone. Essentially, you end up with the same chromic acid that is the active agent to perform the oxidation from a primary alcohol to the carboxylic acid. You can also selectively just oxidize to an aldehyde and then stop at that stage using a compound called PCC, which is pyridinium chlorochromate, I think it's called. Anyways, you don't need to know, just say PCC. It's selective oxidation of primary alcohol to an aldehyde. Oh, I have it right here. Pyridinium chlorochromate. So there is the structure, if you are curious. So a secondary alcohol can also be oxidized, but not all the way to, under these conditions, not all the way to a carboxylic acid, so, or an ester. So this oxidation can be performed by either by any of the conditions that I had shown previously. So the I took this figure from the textbook, and they showed this this oxidation is not possible, but it's not exactly true. You can, as you can see in the previous oxidation ladder, you can oxidize a ketone to an ester by using MCPBA. That is called the Baeyer-Villiger oxidation. Have you guys learned that? Okay, then I won't expect you to know it. But I just wanted to point out that this is not exactly true. So you can oxidize to ester, no problem, under, we'll just call it specific conditions. The reason why the textbook doesn't consider that the same kind of oxidation is because to oxidize to an ester, as they've shown here, you actually have to break this carbon R bond, right? This R is actually ends up being that R, but again, you don't have to know that. So because it involves a carbon bond breaking, or carbon oxygen bond breaking, it's not exactly the same kind of oxidation. But anyways, and then finally, tertiary alcohols, this carbon is already saturated, so you can't really oxidize it any further than that. So really, it's just primary alcohols and secondary alcohols that can be oxidized. Are we good? Oh, DCM is dichloromethane. It is a solvent. So basically, it's a non-polar aprotic solvent. So we can also go the opposite direction. So we can reduce carbonyl containing compounds. And I'm sure you guys have learned about sodium borohydride and lithium aluminum hydride. And actually, this is an example of chemoselectivity that you would have seen in your previous studies. So first, let's define what chemoselectivity is. So chemoselectivity is the preferential reaction of a chemical reagent with one of two or more different functional groups. So essentially, it means that if you have multiple functional groups that can be affected by a reagent, but a reagent is considered chemoselective if it can only react with one of them selectively over the other. So in the case of sodium borohydride, that sodium borohydride is not chemoselective because it reduces both ketones and esters. Oh, sorry, it is chemoselective because it only reduces the ketone but not the ester. So sodium borohydride can give the chemoselective reduction, but lithium aluminum hydride is not chemoselective because it reduces both the ketone and the ester to give the alcohols respectively. So whenever in other reactions that you'll learn throughout the course, there will be some chemoselective aspects to it. So make sure you always keep an open mind and remember, is this reaction selective for just one functional group, or does it affect multiple different functional groups as well? And here you can see, apart from just sodium borohydride and lithium aluminum hydride, there's also a whole bunch of other borohydrides that have varying degrees of selectivity. So ketones and aldehydes tend to be the most reactive, but acids tend to be the least reactive, and you can kind of tailor the reactivity that you want just by changing the borohydride that you use. I don't expect you guys to know to memorize all the things that aren't highlighted, so you don't have to know those. But just know that lithium aluminum hydride reduces pretty much everything. Sodium borohydride can only reduce ketones, aldehydes, and acid chlorides. It doesn't touch acids and esters. Oh, I want to add that this is described in Klein 1210. And this is also Klein unit 12 as well. There's also one more reagent. So have you guys heard of this reducing agent called Dibal? Okay, well, I'm hearing mixed signals. It stands for diisobutyl aluminum hydride. The H just refers to that hydride part. Sometimes you'll just see it as called Dibal, or the L is lowercase. But essentially the formula looks like that, but it actually exists as a dimer. And Dibal is special because it can selectively reduce 2-aldehyde. But it requires strict temperature control. So we can have either esters or carboxylic acids. And in the presence of Dibal, we can reduce it to the aldehyde. So this requires a protic solvent, because otherwise if you were using a protic solvent, that would decompose your Dibal, or toluene DCM, like we discussed earlier. And we require low temperatures. So do you know how we can achieve minus 78 degrees Celsius in a lab? Did you guys learn that? Yeah, so when you combine dry ice and acetone, you get a cooling bath that cools to minus 78 degrees. And that allows you to do reactions that are very reactive, but in a controlled manner. Dry ice is just solid CO2. So this is a very useful reagent to have in your toolkit to selectively generate aldehydes from carboxylic acids or esters. Any questions on oxidations, reductions of alcohols? Yeah. When you use Dibal at a higher temperature, it just directly reduces all the way to the alcohol. Yeah.
And then also, that's a relative term, right? So like NADH4, if you have a molecule with ketone and aldehyde, it's not.
Sorry, if you,
Like, it's a relative term relative to the molecule you're talking about.
yes.
Like NADH4 is not just chemoselective, you have to talk about it in reference to another.
Well, chemoselectivity is always in the context of one of two or more different functional groups. So you would always be comparing between functional groups. Any other questions? Okay, so another example of chemoselectivity is in catalytic hydrogenation. So typically we can reduce alkenes and nitro groups very easily. Nitro groups, of course, look like this. And when they are reduced, we get amines. So these are the most reactive under catalytic hydrogenation conditions. The next would be carbonyl groups, followed by aromatic rings. Aromatic rings, of course, are very stable, so they're not very reactive, but they can be fully saturated under catalytic hydrogenations, especially if you use really high temperature and pressure. So catalytic hydrogenation can be chemoselective. If you just consume the alkene, the alkyne, and the nitro groups first under lower pressure, lower temperature conditions. So that allows you to chemoselectively reduce these functional groups in the presence of carbonyl groups and aromatic groups, because these require more higher temperature and higher pressure to achieve the same transformation. You can also do a chemoselective reduction of alkynes, which I described earlier. So chemoselectively reduce to the alkenes and not have these alkenes react any further. So when you use Lindlar's catalyst, you get chemoselective reduction of the alkyne to the cis alkene. Lindlar's catalyst, as I said before, it is palladium immobilized on either calcium carbonate or barium sulfate. And it is poisoned with lead, sulfur, or even organic molecules like quinoline, just to reduce its reactivity so that it stops at this alkene stage and doesn't go further. No worries. So we can also selectively get the trans alkene by using a dissolving metal reduction as well. So these are just two examples of chemoselectivity. You also come across regioselectivity. Oh, yeah. It can be as well. Actually, this is an example of both chemoselectivity and stereoselectivity. And it's not the presence of one means it can't be the other. And that's a very good point. I wanted to bring that up later, but since you are talking about it now, this is also an example of stereoselectivity. Because you can selectively form a cis alkene versus a trans alkene. So in the sense of your product distribution being selective for cis or trans, that indicates that it's stereoselective. In the sense that you can only react to the alkene and not have it react further, that is what makes it chemoselective. So it's both. And I actually want you guys to critically consider reactions as you come across them, because they can be all of these things: chemoselective, regioselective, and stereoselective, or none at all, or some of them. So anytime you come across a reaction, kind of have at the back of your mind, ask yourself, is this chemoselective, or can I make it chemoselectively? Does this only react at a certain position? Is it regioselective, or does it give me a certain stereochemistry? It would be stereoselective. So I'll go through those last two later on as well. So regioselectivity, you've come across several reactions that are regioselective. And that essentially just means preferential reaction at a desired position of a molecule with more than one reactive site. So one good example of that is epoxide ring opening. You selectively have the nucleophile, or the nucleophile selectively attacks at this position because it's less hindered. And that even though we could theoretically attack at this position here, but that doesn't happen. So this is one example of a regioselective epoxide ring opening reaction. We also talked about a Markovnikov or an anti-Markovnikov product. That is also an example of regioselectivity, whether your bromine is on the more substituted carbon or on the less substituted carbon. The Zaitsev or Hoffman product is also an example of regioselectivity. You can select for the less substituted alkene by using a bulkier base. So that is how you can control the regioselectivity of a reaction. Can you think of any other examples that we talked about that are regioselective? We maybe scroll back to some slides. Yeah, so those Markovnikov, anti-Markovnikov, essentially any reaction that gives you a Markovnikov or anti-Markovnikov selectivity can be considered regioselective. These reactions here too, like halohydrin formation, the bromine always goes on the less substituted carbon, the OH on the more substituted carbon. So that's also regioselective. Again, Markovnikov, anti-Markovnikov. This is an example of regioselectivity as well, depending, being able to control which regioisomer you form. You've also learned electrophilic aromatic substitution, right? Yes, no, like para-directing, meta-directing. Yeah, so with certain directing groups on your aryl ring, you can have different products being selectively formed. So that is also another example of regioselectivity. And then finally, we have stereoselectivity, the definition being the preferential formation of one stereoisomer over another. And in stereoselective conditions, you typically form a mixture, but one of them is favored over the other. So one of them is major, the others are minor. That's what we consider selective. So in this E2 reaction here, we can form, if we have deprotonation here, we can form either the transalkene or the cisalkene, but the transalkene is actually favored because it is just the more stable alkene. So this reaction, this E2 reaction here is stereoselective. Do we have Zaitsev or Hoffman products in this case? Why is that? Yeah. So whether we deprotonate here or here, we still form a disubstituted alkene. So here, this alkene has two substituents. This alkene also has two substituents. So in fact, both are the Zaitsev product. And in fact, this kind of gives you an example of why you should evaluate every reaction on its own merit rather than try to memorize, oh, elimination reactions always give Zaitsev or Hoffman, because that's not always necessarily the case. In this case, the transisomer is more stable, so it's favored. This example is in 7.8 if you want more information on that. Stereospecific reactions are a subset of stereoselective reactions, but additionally, the reactant is stereoisomeric. So your starting material has a stereocenter, and the reaction outcome depends on which stereoisomer is used. Yeah. This is the third. Yeah. Most of you have the third, right? Yeah. So stereospecific reactions are a subset of stereoselective reactions, but the reactant is stereoisomeric, and the reaction outcome depends on which stereoisomer is used. So this is another example of an E2 reaction that is actually stereospecific. And it's stereospecific because we can only form this alkene. The other alkene can't be formed. So let me walk you through why that's the case. So if we redraw this starting material in the Newman projection, looking down that carbon-carbon bond. We have the hydrogen there, methyl group there, phenyl group there. And then in the back carbon, we have bromine on top, hydrogen there, and tert-butyl there. So I don't know if you've learned, but for an E2 reaction to take place, the dihedral angle of the hydrogen carbon-carbon bromine has to be in an anti-configuration. So that's 180 degrees. So this is called anti-periplanar. An anti-periplanar geometry is required for an E2 reaction. So you can imagine when these two groups are eliminated, kind of the molecule here flattens to give you the alkene. The only isomer that can be formed is this one, because if you rotate this bond here and you put the hydrogen and the bromine now on the same side of the molecule, so this is essentially the conformation that is required in order to generate the opposite stereoisomer here, where your tert-butyl is now on this side. See, do you guys see that? So this tert-butyl would be where the hydrogen is, and this hydrogen would be where the tert-butyl is. So that would be the opposite isomer. But in order to generate that alkene isomer, you would have to have the hydrogen carbon bromine bond to have a 0 degree dihedral angle. And that would not give you a productive E2 reaction because it doesn't give you the proper anti-periplanar geometry that is required. So this conformation is actually not reactive. Not reactive towards an elimination reaction, which is why this specific E2 reaction is a stereospecific transformation, because you can only get this alkene isomer from the starting material. Of course, you've also learned that in an SN2 reaction, if you start with an electrophile that is just one stereoisomer, you would get inversion of stereochemistry upon attack of your nucleophile. If it's an SN2 type mechanism, which in this case it is. But that's only if you start with a stereoisomeric compound, right? Because that is one of the requirements for a stereospecific reaction, that your reactant is stereoisomeric. Yeah. So I just want to point out that in these two examples, we saw a stereoselective E2, a stereospecific E2. So that means it can be either, it can be or. So you have to evaluate each reaction as you come across them. We also saw the alkyne reaction can be chemoselective and also stereoselective. So once again, it can be both. So it's really important that you kind of look at every chemical transformation on a case-by-case basis and then evaluate whether it's stereoselective, chemoselective, or regioselective. Any questions? Okay, so just to wrap up the functional group reactivity, so reactions on carboxylic acids. So with a carboxylic acid, you can generate an acid chloride by using thionyl chloride, like that. That's what an acid chloride looks like. You can also hydrolyze it back with base or water to give you back the carboxylic acid. You can do a peptide coupling with an amine and DCC to give you the corresponding amide. You can also get the amide from an aminolysis with the acid halide. Hydrolysis of the amide also gives you back the carboxylic acid. And then with an amide, you can dehydrate it to give you a nitrile, or you can hydrolyze it to give you back the amide. And then finally, you can generate an ester from a carboxylic acid by reacting it with an alcohol in the presence of an acid. This is called a Fischer esterification. And the reverse reaction is just the ester hydrolysis. So you free up the alcohol that is here and the carboxylic acid after you do the ester hydrolysis. Did you guys learn carboxylic acid chemistry? Okay, so this is not foreign to you. Then I suggest review. There's also one more set of reactions. Do you guys know how you can form? Well, first of all, what is this functional group here called? Yeah. Do you know how you can form it? Essentially, you can react it with an acid chloride, or you can react it with a symmetrical anhydride. So essentially, what I've drawn in squares are the leaving groups. You have, and then technically, whenever you're reacting with a carbonyl, you always get a tetrahedral intermediate and then collapse of the tetrahedral intermediate before you have the leaving group leave. So I'm going to just abbreviate it like that. So formation of the tetrahedral intermediate and then collapse of the tetrahedral intermediate and then leaving of the chloride. And then that is what gives you your anhydride. And it's analogous reactivity with this carbonyl here for the for reacting with the anhydride. Any questions about this? Yeah. No, yeah, it's just to show that this R group is different from this R group. Okay. So all of this brings us to synthesis, which is the entire point of organic chemistry, to build molecular complexity with sequential reactions. So if we want to generate this isomeric bromide from this bromide here, we can go through an elimination reaction to generate an alkene and then add our bromide in an anti-Markovnikov or Markovnikov fashion to generate the isomer that we want. So essentially, I'm just going to walk you through all the options that we have. So starting with this bromide, if we use a less hindered base, then we can get formation of which alkene is this, the Zaitsev or the Hoffman? Yes, because it is the more substituted alkene. Less hindered base gives the Zaitsev product. Or we can use a more hindered base to give the Hoffman product. With the Zaitsev product in hand, so the more substituted alkene, if we want to generate the desired bromide here, the tertiary bromide, we would need our bromine to attach to the more substituted carbon. That means we want the Markovnikov product to form. And we know that to generate the Markovnikov product, we just can do a simple HBr addition across the double bond, and that will give us the Markovnikov product. So from this alkene, we can only add a bromine at this position or at this position, which is not what the question initially asked for. So in fact, we cannot get to the desired product from this alkene. But what we can get to, for example, if we want the bromine on the less substituted carbon, that is the anti-Markovnikov product. And we can achieve that by doing the radical-based HBr addition. So HBr in the presence of the peroxide. So the entire unit 11 of Klein goes through this whole process. And I think it's a very important read. So this is another example of a synthesis kind of question. Yeah. Let's walk through that. So you would have, so your first step would be deprotonation of either here or here. Oh, okay. How would your hydride shift occur? You know what? I'm going to get back to you on that. But for now, let's assume hydride shifts and all that stuff don't really apply in this case. Okay, so we can go through an analogous sequence of events with alcohols as well. So if we want to generate this alcohol from this starting alcohol here, can you imagine like an alkene intermediate that we can go through to get there? Where would we put a double bond that can allow us to transfer the location of the OH.
Carbons 1 and 2, I think to the left.
Yeah, so these two carbons here. So we can go through an intermediate like that to get to the desired product. So to get from this alcohol to this alkene, it's an elimination, but we can't just do an E2 or whatever. We can't do an elimination reaction directly from the free hydroxyl group. We actually have to convert it to the tosylate first. We have to make it a good leaving group. So that's reaction with tosyl chloride and pyridine. Pyridine is just acting as a base. And then you can do your E2 reaction. So in this case, we are generating the Zaitsev product. So we can use a less hindered base for that. And then we want to generate the Markovnikov alcohol. So that is just a simple acid catalyzed process, or we can do the oxymercuration, demercuration process. When you review these notes later, you can kind of scroll back to the earlier slide when I had all those reactions in the big circle and kind of see for yourself that this alkene to get this more substituted alcohol is these conditions. And then you can kind of practice in that sort of way. And then just for practice sake, we can also generate the anti-Markovnikov alcohol from this alkene by using hydroboration, oxidation. So those are the conditions for that. And then just for sake of exercise, we can think about how to generate this isomeric alcohol as well. And this one can be generated from the Hoffman product. So how can we generate the Hoffman product from this alcohol? What base would we use? A hindered one or a not so hindered one? Yes, you would want to use a hindered base. What's an example of a hindered base? Potassium terbutoxide, perfect. But we can't react this directly with the alcohol. We have to turn the alcohol into a good leaving group first. So in fact, the elimination is our step 2. Our step 1, what is our step 1? Yeah, we want to tosylate that. We want to turn that into a good leaving group first before we do the elimination reaction. So this is the Hoffman alkene. And then here we are forming the anti-Markovnikov alcohol. And to get that, we do hydroboration oxidation, same as here. So that is that. So it all comes together. Okay, so this is essentially the synthesis toolbox that you have. It summarizes all of the functional group interconversions that we had discussed today that you had learned in the first 2 years or first 2 semesters of your organic chemistry classes. Additionally, we also have learned oxidation up to carboxylic acid of alcohols, and then reduction down to alcohol. And we also learned interconversion of carboxylic acids. So that is essentially the toolbox that you have to work with whenever you are conjuring up some syntheses. So I have some practice problems here for you to try out. Basically how you can generate these compounds here from the respective starting materials here. One important thing that you want to note, you want to note two things. First is whether there's any change in the number of carbon atoms. So I'll just walk you through that. So in this first example, we have 1, 2, 3, 4, 5 as our longest chain, 1, 2, 3, 4, 5. And we have this dimethyl group in carbon 3. So our carbon skeleton in this example doesn't change. In this example, we start out with a 4-carbon molecule and we end up with 1, 2, 3, 4, 5, 6. So somehow we have to think of a way to add 2 carbon molecules here. And then the next thing you look at is change in identity or location of a functional group. So here you have a geminal dihalide, which then turns into a ketone. So that kind of tells you a hint of what kind of reactions are required there. Here you have to think about how you can add that 2-carbon fragment and then how you can transform that 2-carbon fragment to an epoxide. So I'm going to give you a little bit of time to try to figure out these 2 questions based on the synthesis toolbox that you guys have.
Scroll up to what?
Okay. So did you guys find these questions difficult? The second one's difficult? Okay. All right, well, let's walk through it. Okay, so whenever you see like a dihalide like this, it's a really big hint that we're going to go through some sort of alkyne intermediate. So how can we generate an alkyne from this geminal dibromide? We can use excess sodium amide as step 1, and then as step 2, we have water. So I would expect you to memorize these specific conditions and the order of steps required to generate the desired intermediate. So that'll give you the alkyne. And then we can go directly to the ketone from an alkyne, shown here. So this is just that acid catalyzed hydration of alkynes. And the conditions for that, I would expect you to memorize. So it's water, sulfuric acid, and mercuric sulfate. Did you guys get that? Yeah? Awesome. Okay. So I described before that we're somehow adding a 2-carbon fragment to this 4-carbon starting material. You really so far only know two carbon-carbon bond forming reactions. The first being the displacement, SN2 displacement with cyanide. But that's just, cyanide is just one carbon. So the other carbon-carbon bond forming reaction that you've learned is here. So basically you can deprotonate the terminal alkynes. You can deprotonate that proton in the presence of sodium amide, and that gives you the alkynide, acetylide, I guess, if we were dealing with two carbons. So your first step would be to start off with this alkyne and then react it with sodium amide. One equivalent is necessary, so you don't have to show that explicitly to generate this carbanion here. That sodium is kind of understood to be there. And then you can react it with your alkyl halide. And that gives you your 1, 2, 3, 4, 5, 6 carbon skeleton. So how do we generate epoxides generally? Yeah, and what functional group does it react with to form an epoxide? Alkene. So how can we get from an alkyne to an alkene? Well, we have lots of hydrogenation conditions. Let's see, do they show it here? Yeah. So we have shown it here. So to go from an alkyne to an alkene, we can either use H2 and Lindlar's catalyst or dissolving metal reduction with sodium and ammonia. In this case, does the stereochemistry of our alkene matter? No. So it doesn't really matter which method you use. I'm just going to go with H2 Lindlar's catalyst, but dissolving metal reduction would work too. And that's kind of a good thing about these synthetic questions, because there's often multiple answers to the same thing. So lots of opportunities to make up for lost marks. And then finally, that will give you your desired product. So I would say that these are relatively simple synthesis questions. I would, as I had explained in the syllabus, eventually expect you to do up to 10 to 15 step syntheses. So if this seems really hard for you, I would really go through Klein chapter 12, or sorry, 11, unit 11, and go through all of the exercises and everything just to make sure you understand it. But that would be it for today.